All right, let's get right into it. We're going to talk about what might just be the most beautiful, most mind-bending theory in all of physics, Einstein's general theory of relativity. And look, this idea, it didn't just tweak what we thought we knew about gravity. Oh no. It completely tore up the rulebook and told us the universe wasn't some static stage for things to happen on, but a dynamic, curving, stretching fabric of reality itself. You see, for over 200 years, if you said gravity, you were really saying Isaac Newton. I mean, his theory was an absolute masterpiece. It worked for everything, from a simple apple falling off a tree all the way to planets circling the sun. The idea was pretty straightforward, right? Gravity was just this invisible force, kind of like a cosmic string, that instantly, and that's the key word, instantly pulled stuff together no matter how far apart they were. And for centuries, that was it. That was the law. I mean, it worked perfectly, so why question it? But what if that whole idea, the very foundation of it, that gravity is a force, was completely wrong? What if it was all just an illusion?
So that one question, it created a huge problem in physics, a real crisis. And funny enough, it was a crisis that Einstein himself had created. You see, the issue wasn't that Newton was wrong, exactly. It was that Newton's universe just couldn't exist in the new reality that Einstein had just discovered.
So, flashback to 1905, Einstein drops his theory of special relativity, and it basically throws a giant wrench into the gears of physics. And why? Well, it all comes down to one simple, unbreakable rule. There's a cosmic speed limit, the speed of light, and absolutely nothing in the universe can go faster than that. Not a spaceship, not a signal, not even information itself. Okay, so you see the massive contradiction here, right? On one hand, you've got Newton, who says gravity's effects are instantaneous. On the other, you have Einstein, who says nothing can be instantaneous. Just think about it this way. Imagine the sun just, poof, vanished, gone. According to Newton, the Earth would instantly fly off into space, that very second. But Einstein's new rule says, whoa, hold on a minute. Information can't travel faster than light. It takes light about 8 minutes to get from the sun to us, so we wouldn't even know the sun was gone for a full 8 minutes. The two theories just couldn't both be right. Physics was broken. So this massive paradox sent Einstein on this incredible 8-year journey to figure out a new theory of gravity. And the big breakthrough, the aha moment, came from something he later called his happiest thought. And it's a thought experiment I want you to try right now, okay? Just imagine you're inside a sealed room. No windows, no doors you can see out of. Think of it like a little elevator cabin, totally cut off from everything outside. Now, inside this room, you pull a ball out of your pocket. You just let it go. And plop, it falls straight to the floor. Just like you'd expect, right? Nothing weird about that. But now, here comes the big question. So, why did the ball fall? Are you in that little room, sitting right here on the surface of the Earth where gravity is pulling the ball down? Or are you in a rocket ship, way out in the middle of deep space, accelerating upwards at a very specific rate, 9.8 meters per second squared? Think about it. In the rocket, the floor is rushing up to meet the ball. On Earth, the ball is falling to the floor. But from your perspective, inside the box, they feel exactly the same. The wild thing is, there is literally no experiment you could possibly perform inside that room to tell the difference. None. The physics are identical. And this was Einstein's incredible leap of genius, his happiest thought. He realized that if you can't tell the difference between gravity and acceleration, maybe that's because there is no difference. They aren't just similar, they are equivalent. They are, in a very real sense, the exact same thing. And that idea, the equivalence principle, was the key that unlocked a whole new understanding of the universe. And hey, if you think this is all just some weird, abstract thought experiment, think again. The GPS on your phone, the one you use every single day, it only works because it's constantly making calculations based on both special and general relativity. If it didn't account for Einstein's theories, your GPS would be off by miles within a single day. This isn't just theory, it's real-world technology. Okay, so if gravity isn't a force that pulls, then what in the world is it? Well, Einstein's answer was totally radical, but also incredibly elegant. He said gravity is nothing less than the curvature of spacetime itself. The physicist John Archibald Wheeler put it perfectly, probably the best summary ever. He said, "Spacetime tells matter how to move, matter tells spacetime how to curve."
It's this beautiful cosmic dance, you know? The stuff in the universe, stars, planets, you, me, we bend the fabric of space-time. And that curved fabric, in turn, tells us how to move through it. Here's the classic way to picture it, and it's a really good one. Imagine space-time is a huge, flat, stretchy rubber sheet. Now take a heavy bowling ball and place it in the middle. What happens? The sheet bends, it sags, it creates a curve. Well, that's exactly what massive things like our sun do. They warp the very fabric of space-time around them. Now let's bring it back to the Earth and the sun. So what's happening there? The Earth isn't being pulled by the sun's gravity, no. The sun, being so massive, has created this huge curve, this big dip in the space-time rubber sheet. And the Earth, it's just trying to travel in a straight line. But since it's moving through that curved space, its straight-line path becomes an orbit. What we see as an orbit is just the Earth following the straightest possible path it can through a warped reality. And yeah, there's a fancy word for this, of course. It's called a geodesic. It's basically just the word physicists use for the straightest possible line through curved space-time. So when you're in freefall or when a planet is in orbit, you're not feeling a force, you're just moving along your natural force-free path. You're following a geodesic. All right, a theory that completely rewrites the rules of the universe sounds amazing. But the big question is it actually right? Does it match what we see in the real world? Well, let's get into the evidence, because this is where it gets really, really cool. I mean, the proof has been stacking up for more than 100 years now. The first huge confirmation came way back in 1919. An astronomer, Arthur Eddington, watched a solar eclipse and saw that the light from distant stars was literally bending as it passed by the sun, just like Einstein's theory said it would. And then, fast forward to 2015, we got the ultimate proof. We directly detected gravitational waves, actual ripples in space-time caused by two black holes colliding over a billion light-years away. Incredible. And you know, the real power of the theory wasn't just that it explained things we already knew. It was that it predicted things that sounded like pure science fiction at the time. It predicted black holes, places where gravity is so intense that space-time basically ties itself in a knot and not even light can get out. It predicted that massive galaxies could act like giant lenses, bending light. And it even predicted that the entire universe should be expanding, which is the very foundation of our modern Big Bang theory. But, and you know in physics there's always a but, as wildly successful as general relativity is, it's not the complete story. It's not the final word. There's still one huge glaring problem. So here's the deal. All of modern physics is built on two incredible theories. You've got general relativity, which is the rule book for the really, really big things. Planets, stars, entire galaxies. And then you have quantum mechanics, which is the rule book for the really, really small stuff. Atoms, electrons, all those tiny particles. And here's the problem. These two theories, they are fundamentally incompatible. They just don't work together. It's like they're written in two different languages that contradict each other. And when you get to a place where you need both of them at the same time, like trying to describe the center of a black hole or the very first instant of the Big Bang, the math just completely breaks down. It spits out nonsense answers like infinity. It just doesn't work. So that leads us right to the biggest, most profound quest in all of physics today. How do we unite these two ideas? How do we find a single theory, a theory of quantum gravity, that can describe everything from the smallest particle to the entire universe? We don't know the answer yet. But one thing is for sure. Whatever that new theory looks like, it's going to show us a picture of reality that is even deeper and almost certainly way, way stranger than we can even imagine.